Okay, this is the pretest, not 2021, 21, 22, for our stoichiometry test, which will be given on Friday and Monday. So here we go. Number one, aluminum is a metal with a high strength to mass ratio and a high resistance to corrosion. It is often used for structural purposes. Okay, calculate the number of moles of atoms in a 10-gram sample of aluminum. All right, so in this case, we're just going from, let's see here, atoms, moles, and 10-gram sample of aluminum. So we're not converting out of aluminum into something different. We're just simply going from 10 grams of aluminum into moles of aluminum. So I start with the given, grams of aluminum, and to get out of grams of aluminum, I put grams of aluminum down here, and I know that there's a conversion from grams of aluminum into 1 mole of aluminum via the molar mass of aluminum. So the molar mass of aluminum, 26.982. Okay, and when I do that into my calculator, I get an answer about 0.3713 and then some other things. The reason I stopped there is because when our answer, we need to use sig figs. And so when I look at 10, I know that that 1 is a sig fig. This trailing 0 is significant, and that means that 0 in between them is significant. So I have 1, 2, 3 sig figs, which means I need 3 sig figs down here. And this 0 is not significant, so I start 1, 2, 3. There, that 1. That means that 3 rounds that 1, and we keep it a 1. So your answer should be 0.371, and then grams of aluminum. And there is your answer. Okay? Down here, calculate the number of atoms in the same amount of aluminum. So if I want to do some testing strategies here, I know that once again I'm going to have 3 sig figs in my answer, and that my answer should be atoms of aluminum. Okay, and so I can go ahead and box that in to help me remember how to answer. So I'm going to convert 10.0 grams of aluminum, and now I need to end up in atoms of aluminum. Well, if I need to get out of this, and this is not, let me get rid of that real quick. We'll eventually get there, but that's not my next step. So grams of aluminum. All right. Now, because I crossed that out because there's no conversion from grams into atoms. I first need to get into a mole. So that means 1 mole of aluminum. It was, once again, and we used it up here already, to get out of grams, 26.982. That's the molar mass into moles. Now that I'm in the mole, I can get out of moles of aluminum and into atoms of aluminum. And to get into any type of particle, it is 6.02 times 10 to the 23rd. Okay, so when I stick that in, put this into my calculator, and then divide by what's on the bottom, I should get 2.23 times 10 to the 22nd atoms of aluminum. Okay, and all of these zeros here are non-significant. Okay, are non-significant. So 1, 2, 3. There's my amount of sig figs. Atoms of aluminum. That's all necessary. Okay. Number 2. All right, isopentyl acetate, which is this right here. The compound responsible for the scent of bananas can be produced commercially. Interesting, B's released about 1, don't worry about what that unit is because it's converted into grams right here, which is a good thing for us, of this compound when they sting. The resulting scent attracts other bees to join the attack. Calculate the number of molecules, so I want to end up in molecules, which is a type of particle, of C7H14O2. Okay, and I need, from this number right here, it tells me I'm going to have 2 sig figs. Okay, and that is going to be what my answer is where my answer is going to be. So calculate the number of molecules released in a typical bee sting. So what I want to do is convert that into molecules of isopentyl acetate. So I start with 1.0 times 10 to the negative 6 grams of C7H14O2, and I'm going to convert that into molecules. So first I need to get it into a mole. So 1 mole of C7H14O2 is equal to its molar mass. So the molar mass of that is 130.187 grams. So now that I'm out of that, I'm in moles of the acetate. Then I can get out of moles of the acetate and into molecules of the acetate by using 6.02 times 10 to the 23rd. All right, so when I put this into my calculator the right way, I should come out with, and using sig figs properly, 4.6 times 10 to the 15th. All right, molecules C7H14O2. Okay, number 3. All right, number 3. So solid lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide from the living environment by forming solid lithium carbonate in liquid water. Okay, balance the equation is your first step. So the best way to balance this, if we put a 2 here, that makes everything else work. Okay, some of these get a little bit complicated, but if you break down each element and put the numbers out here and balance on both sides, you come out with 2. The rest of these are implied ones, but if you want, you can go ahead and put the ones in. Now, what is the mass of gaseous carbon dioxide can be absorbed by 25 grams of lithium? So what we want to do is turn 25 grams of lithium oxide into gaseous carbon dioxide. Okay, so we want to convert this amount into that amount. So to do that, we start with 25 grams of lithium oxide, and now we need to get out of grams and into the mole, because we're going to be eventually using our molar ratio. We need to get out of grams and into moles so we can use that molar ratio. So that means grams of lithium hydroxide will give me 1 mole of lithium hydroxide. So that this is where your molar mass comes in, because we're talking about a mass here, which is 23.948. That cancels that unit out. Now I'm in moles of lithium hydroxide, so that means lithium hydroxide needs to come down here. Moles. And from here, I can use my molar ratio step to go from moles of lithium hydroxide into moles of carbon dioxide. This is where your molar ratio comes into play, so that is 2 to 1. That unit cancels out. And because I'm asking for a mass, that means I need to end up in a grams over here. So I need to turn 1 mole of carbon dioxide into a mass of carbon dioxide. So I need to use the molar mass, which is 44.009. And when I do all of this, let me see where my work is. When I do all of this the right way, I get 23 grams per mole of carbon dioxide. 2 sig figs, 2 sig figs. Okay? On the back. On the back, once again, my first step here is to balance this equation, and when I do that the right way, I get a 2, I get a 3, that'll be an implied 1, and then 3, 3. Oh, sorry, there we go. Okay, and then coming down here, a sample of 18.1 grams of NH3 is reacted with 9.4 grams of CO2. Circle the limiting reactant. So in this case, I've got to take both of these things into one of the products. Okay. Now, if I read a little bit further, it says how many grams of N2 will be formed, which means the best thing for me to do is to turn each one of these amounts into nitrogen. Now, I technically could turn them into copper or water and still find the limiting reactant, but if I turn them into nitrogen right away, that'll help me answer this question right here. Okay, so when I do, let's see here, this process, I start with 18.1 grams of NH3, and I need to get out of grams of NH3. So I used a molar mass of NH3, which is 17,031 grams of NH3. That equals 1 mole of NH3. That's gone. Then I know that I can use my molar ratio to get out of NH3 and into moles of N2 by the molar ratio, which is 2 to 1. Now I'm out of moles of NH3. Now I need to get out of moles of N2. So 1 mole of nitrogen is equal to the molar mass of N2, which is 28.014 grams of N2. So what I'm going to do here is this answer of 14.89 grams of N2. What I'm saying is if all 18.1 grams of NH3 were to be reacted and go completely away, that means I possibly could make 14.89 grams of N2. But we don't know if that's the case yet or not, because we don't know if we have enough copper oxide to react with this amount of ammonia. Okay, so what I need to do is do this exact same process, but now I'm going to use this copper oxide. So down here, 90.4 grams of copper oxide. Once again, it's the same steps, and now I should get a certain amount of nitrogen from that amount of copper oxide. So to get out of grams of copper oxide into moles of copper oxide, I need the molar mass, which is 79.545 grams. That cancels that unit out, and now my molar ratio step. I know that moles of copper oxide into moles of nitrogen is 3 to 1, like so. That cancels moles, and now I'm in nitrogen, which is a good thing, but now I'm going to turn that nitrogen into a mass of nitrogen by using the molar mass. That cancels out. And now I'm left here, and when I do this math, I come out to have 10.6 grams of nitrogen. So what I'm saying is if all of copper oxide will be used up, then I could possibly form 10.6. If all of ammonia is used up, then I'll get 14.89. Now, we can't have both of these because one of them will get used up before the other one. So in this case, this right here, because it's the lower number, will be the most product that can be produced from these given amounts of material, which means that when we go back to here, well, this was my copper oxide. That means copper oxide is my limiting reactant. Because here it says circle the limiting reactant, so you could have circled it here, or you could have circled it here. Okay, then this question, how many grams of N2 will be formed? Well, when we ran both of these to the possible amounts of nitrogen gas, this was my limiting, so this is my answer for the most possible nitrogen that can be formed from this amount of materials. Okay. Number 5. Very similar question, but first we need to balance it. So when I balance it, you'll have a 2 here, and then an implied 1 here and here. Now, what makes this question difficult is that we have kilograms here and here. Now, we do need to convert those kilograms into grams first, because if you notice up here, all of our molar masses are in in grams. So we need to first convert these into grams. So my first step should be 60, if I'm going to convert, calculate the theoretical yield when 68.5 grams of carbon monoxide is reacted with 8.6 kilograms of hydrogen gas. So your theoretical yield is just a quick way of saying what is your limiting reactant amount. So up here in this question, this was my theoretical yield for this question, okay? It's the same thing as how many grams of N2 will be formed. This is my theoretical yield. So I'm going to be doing the same process down here, except now we're going to call it theoretical yield. So that means 68.5. To turn that into, this is kilograms. To turn that into grams, then I just say, well, 1 kilogram is equal to 1,000 grams. Same thing down here. 8.60 kilograms of H2 is equal to 1 kilogram over 1,000 grams. So now I'm out of kilograms and I'm into grams of each. Okay. Now I can move forward with the math of this. So I need to find a limiting reactant, which means I need to turn the grams into moles. So the molar mass of carbon monoxide is 28.01. That's grams of carbon monoxide. That'll give me 1 mole of carbon monoxide. Then to get out of 1 mole of carbon monoxide is the molar mass of that methanol, which is the molar mass of that is 32.042. And when I do that math, I get something like 78,400 using sig figs. There's 1, 2, 3, 1, 2, 3, and this is grams of carbon monoxide. I need to do the same thing for hydrogen, which means I've already converted it into grams, so now I can get out of grams and into methanol. So I need to get out of grams by doing the molar mass of H2. That'll give me 1 mole of H2, right? Then I can get out of moles of H2 and into moles of carbon monoxide by the molar ratio, which is 2 to 1. And now I can get out of moles, 1 mole of carbon monoxide is equal to the molar mass, which we've already found up here, 32.042. And when I do that math, I should get about 68,300 grams. Okay? So a couple things. Before we do any more converting, these numbers are grams of CO. These are both in grams, both of CO. So now I can compare these, which means this is my lower number, which means H2 is my limiting reactant. So the question is calculate the theoretical yield, which is this right here. Now I would have accepted 68,300 grams, or you could have put 68.3 kilograms of carbon dioxide. Either one was fine. Or you could have put 6.83 times 10 to the 4th grams of carbon monoxide. All three of those are virtually are the same answer, just slightly different forms. Okay, so down here, if 3.57 times 10 to the 4th grams of methanol is actually produced, what is the percent yield of methanol? So we're still using this right here, and we want to find the percent yield, which is the actual over the theoretical. Your actual is what's being produced in a lab. Your theoretical is what the math tells you or what is calculated. Okay? So in the question, here is your actual amount. So that's going to go on top, 3.57 times 10 to the 4th. theoretical comes from right here. We just figured that out. So because this is in scientific notation, I'm going to put this scientific notation down here, but really any one of these numbers put down here will give you the same answer. So 6.83 times 10 to the fourth. And when I do that and multiply it by 100, I should get a percent of 52.3%. Why is it 52.3%? Because 1, 2, 3 sig figs, 1, 2, 3 sig figs. There's your answer. I hope that helps.